Well, thank you, Per. First of all, it's an absolute honor to be here and speak here, and I want to thank you all for this. Also for a fantastic week. I mean, yeah, the boat trip, all the dinners, the dancing, you know, everything. It was just fantastic. I really, really enjoyed it. Before I'm going to talk, maybe I should say something personal also to Sarah and David, because they have played such a big role in my science life. When I was young and was doing my PhD and my postdocs, I was working on radio galaxies, on gigahertz peak spectrum radio sources. I'm sure many of you know about this type of source. I won't dwell on that, what that exactly means. It was very nice. But after some years working on this, I really felt I missed something, and it's really astronomy, the way I pictured it as a young kid, is this really the life for me? And then I purely accidentally stumbled upon Sarah and Dave's work. The beautiful sodium measurement on of HD 209 and everything around it, and I was flabbergasted. I thought, wow, this is what the kind of work that I dreamed of I would be doing if I would be an astronomer later when I was big. So I left everything behind, I changed fields, I didn't look back, and I moved into exoplanets, and I enjoyed it ever since. So now thinking about what would have happened if I your work would not be there, I guess I would have left astronomy, I would have gone into finance, personal business. You know, thinking about it, I would have had my private island, I think, by now. So thank you for pointing me the way to this. Yes. All right. So since I'm the first speaker, maybe I should give also a little bit of a historical overview. You know, it's really this exoplanet field is a revolution that started about 30 years ago. First in 1992, when the first planets were found around a neutron star, and then really the revolution started with the first Jupiter planet around a solar-type star, 51 Peg. Of course, the Nobel Prize were given to that. And that started off here, sort of, that this is a timeline of what are the breakthroughs over the last 30 years. You know, the first transits, the first atmospheric measurement, thermal emission, thermal maps, and so on, up to exo-Earth. And if you think about, you know, which this is quite amazing, the parts that both Sarah and Dave played a role in, you know, I just put sort of the arrows where they had a major part into it, often even leading this stuff. It's just over the whole timeline. So this is absolutely fantastic. A part of that, of course, you know, that you have been so important for the field, but there is also another aspect, and that is you have to realize that this is also for a large part driven by engineering, right? If, for example, if I think about radial velocity measurements, which were very important for the first few years, and even up to now, a very important part of exoplanet observations from the 1980s until now. Measurements have improved by more than a factor of 1,000. So these are the kind of engineering that is really driving, pushing the field forward. Also, for example, with the Hubble Space Telescope, and now very much with the James Webb. Now, what is nice thing, because now this engineering takes part, now building new instruments takes a long time, often the biggest instrument, multiple decades. Now we can also look forward. You know, we already know what is going to happen in the next 5 or the next 10 years. And that's what mainly my talk is going to be about. What are we going to do in the future? And mainly I'm going to focus on the ELT, the Extremely Large Telescope, on finding new Earth, atmospheres of Earth, and then in the end maybe can we find evidence for life? All right, but why are we all doing this? No, why are we studying exoplanets? And sometimes when I give public talks, I get questions. So what is interesting? What is so interesting about knowing a world, thousands of light years away? Well, I think the answer is it's not about the worlds far away, but these worlds are going to teach us something about ourselves, about the Earth and the place of the solar system in the universe. You know, how do planets form? What kind of architectures of planetary systems are there? How do they relate to the solar system? Are we something special or not? How does the solar system fit into this whole scheme? And then maybe the $1 billion question, do other life-bearing planets exist? And I think there's a very important philosophical aspect to this. But I think it can really change the way humanity thinks about themselves. And I like to see that, 500 years ago, when Galileo and others find out that the Earth is not the center of the universe, it's the sun, and we orbit the sun, and the sun is just a star in the Milky Way. This really changed the way humanity thinks about themselves. I think Darwin is another example, right? Darwin, evolution, it changes the idea how humanity looks at themselves. And I think finding evidence for extraterrestrial life will do something similar. So what we can do first, before we're going to look at the exoplanets, is, of course, there are these planets, there are these worlds that we know very well, and that are the worlds in our own solar system. Now, when you look at the planets in the solar system, you already learn very quickly that they show an immense complexity and diversity. Already, if you take the 4 planets and moons that have an atmosphere, Venus, Earth, Mars, and Titan, you see they are very different. Venus has a very thick CO2-based atmosphere with opaque sulfuric acid clouds. Earth is nitrogen-based. It has a partially clear atmosphere. It has a lot of biotic oxygen. Mars has a very thin atmosphere, CO2-based. And Titan, again, is again nitrogen-based, very opaque methane and ethane clouds. So what's actually happening here? All these different worlds, the 4 worlds that we know are so different. What are their relationships? Do we understand anything why Earth, Mars, and Venus are so different from each other? And the way I like to see that is if I go back to Darwin, one of my heroes. What if Darwin only knew about 3 different species, an owl, a scorpion, and a monkey? Would he find out all this important work about the tree of life? No, I don't think so, right? He understood, he went on this epic journey on the Beagle, along all the shores of distant worlds. And only after gathering all this data of all these different things, he started to a certain picture start to actually emerge. And this is the way I see the exoplanet field as well. We're going to study all these distant worlds, and it's going to be very difficult. It's going to be a very hard journey. But in the end, we will need that to get an emerging picture of what is happening elsewhere, but also in our own solar system. Okay, and where are we now? We have 30 years of exoplanet studies. Now, I think the first lesson is that the actual diversity and complexity is even much larger than we know from our solar system alone. If you think about types of planets that we find, hot Jupiters, so these are gas giants in very short orbits, only a few days. We have super Jupiters. These are planets at up to hundreds of AU distance, several times the mass of Jupiter. How they are formed is not clear. And then we have super Earths or mini Neptunes, something in between the Earth and Neptune, which we thought, actually before we started to study exoplanets, we thought it was logical. There was nothing in between Neptune and the Earth. It turns out the most common planet is actually of this type, or this class. We don't know. It's probably not a single type. It's a whole scala, a whole range of different objects. Now, what we also have learned that exoplanets are very common. Now, this is also realized. Before we started exoplanets, we didn't know how often a system like our own solar system would actually emerge around other stars. Now, these are just some estimates here, but about 1 in 10 stars, probably a bit more, host a Jupiter-mass planet. About 1 in 5 stars have Neptunes, and actually most stars host Earth-mass planets. And I don't mean an Earth in an Earth-like orbit, but really at a random orbit somewhere. So thinking about the solar system, you could say we already in the solar system have 2 or 3 Earth-mass planets. We have Venus, Earth, and Mars. And what's nice thing, because these Earth-mass planets are so common, you see them already around very nearby star, and our nearest neighbor is Proxima Centaurus. And a bit less than a decade ago, a planet an Earth mass planet was found around our nearest neighbor, Proxima, in a short orbit, 11 days. And then you think, oh, wait, 11 days, that must be very hot there. No, Proxima Sun itself is 1,000 times less luminous than our sun. And what that means actually, that the 11-day orbit, it's at such a distance from its host star that it receives as much energy as a planet in the solar system would between the orbit of Earth and Mars. So it could well have water, it could have oceans. We don't know, but this is really exciting that there is a planet around our nearest neighbor star that could be similar to our own Earth. Now there are other, we know now that around these small dwarf stars, rocky exoplanets, temperate Earths are very common. You know, there's the famous the TRAPPIST-1 system found by a Belgian research group with 7 transiting planets, and 3 of them may be in such a distance from the host star that they could also have liquid water on their surface. I will tell you a little bit more about the TRAPPIST system later. Now, if we think, no, you find these planets, what do we need to do now to start to learn more about the planet? Now, what kind of questions can we ask ourselves? And I think the first question to ask is, what is the bulk buildup of the planet? Does the planet have an atmosphere? What is the atmosphere made of? What is its climate like? How cold, how warm? What is the day side? What is the night side like? And do we understand that all in the context of its formation and evolution? And do we understand all the physical and chemical and possible geological processes that happen on these planets? Now, if you then zoom in on the Earth-like planets, then you can ask more questions like, you know, is there any water? Now, that's of course interesting if we think that water is needed if you want life to actually start. Are there any biosignature gases, like we really like molecular oxygen, or maybe methane or ozone? And then the most difficult question will be in the future, are these biosignatures due to biological activity or not? And for example, you know, oxygen, all the oxygen here on Earth in the atmosphere is purely because of the biological activity here. The hope is that we can see oxygen also on other planets. Does that mean that will also be caused by biological activity? The answer is no. No, there are already, I'm pressing the wrong button all the time. There are already several different theories about how you could also build up oxygen, molecular oxygen in the atmosphere without life. For example, if you have an abundant ocean and that boils partly off and the hydrogen escapes into space and the oxygen leaves behind. That's also a way to build up oxygen. But hopefully we can actually separate the different scenarios by understanding the whole scala of different molecules that are present in these objects. Very briefly, for those who don't know, so how are most of these measurements done? These are all transiting systems. So what happens at some point, the planet moves in front of the star, blocks off starlight. This is the way that we find the system. But also a little bit of starlight is filtering through the atmosphere. And due to absorption and scattering process, you can measure the change in light, the change in spectrum, and from that derive what atoms or molecules are present. Then half an orbit later, we have eclipse measurements. The planet is eclipsed by the star, and any light coming from the planet, any emission, you can then measure to be actually gone. That can be thermal emission, or it can be scattered light. And then we have also, during the orbit, we can observe variations by phase. For example, here around the transit, we look at the night side. Here we look at the evening side, and that is more the midday. And then here is the morning? I don't know. Morning, evening side. One of the two. So there are basically 3 ways of doing it. And what is nice, of course, is that Dave and Sarah have been involved in all of these measurements for the first time. Both the transit, eclipse, and also the phase variations, making a thermal map of the first planet. Now, this is another way of looking at this journey I was talking about. So what can we learn about this planet? And what I like about this plot, you plot here temperature of a planet versus the planet mass. And here the gray circles are the planets in our own solar system. So we have Jupiter and Saturn. These are gas giants. It's mainly molecular hydrogen and helium. We have Neptune and Uranus, also hydrogen, helium, and rich with some metals. We have the Earth. We have Venus, which are quite different in the composition, very different. We have Mars, which has a very small atmosphere, and then we have Mercury and our moon I put here as well. So these are airless bodies. And then you can think about, processes that could cause the actual differences between these type of atmospheres. So, for example, people may think that the difference between the Earth and Venus is due to a runaway greenhouse effect that actually affected the atmosphere of Venus. You need a minimum mass to form, to have enough mass to actually, during the formation process, to actually attract hydrogen and helium gas, so to make gas giant planets, but also to hold on later in the life, to hold on to the actual hydrogen and helium envelope, so that should be somewhere a limit here. There is, when you go to the hotter and there's here actually a part where the surface gravity is not high enough to keep on to the actual atmosphere, the hydrodynamical escape limit, or maybe due to stellar activity. And then, but when you then get to hotter and hotter planets, then you can have surface melting, through which you also get a secondary atmosphere. Now, what is important to realize, after David Charbonneau's first measurement for the first 20 years, the only planets we manage, almost all planets that we manage to measure, are in this part. Very hot gas giant planets. Hot Jupiters or super Jupiters that are very far away from their host star. And only a few years ago, when the James Webb was launched, very excitingly, then we start to eat into this diagram. And the first thing that we will meet is this part here, and I just, you realize these are just question mark. I just put in something there because we really don't know what is going to happen. These are these super Earth, mini Neptune type of planets, and really it will depend on the composition, the bulk the composition of the planet, what kind of atmospheres probably are seen there. Now, I want to give a few examples of, very briefly, a few examples what the James Webb over the last 2 years has done, which planets are starting to occupy this diagram. We have a very famous planet, K2-18b, a controversial planet, I can tell you. It started off with observations with the Hubble, where two groups found there to be water. And maybe it's nice to realize what is the difference between Hubble and the James Webb. You could see this atmosphere as a kind of a room, and we want to know what is in the room, but the actual door is closed. What we could do with the Hubble is we have the keyhole, and with the Hubble we look through the keyhole to see what is in the actual room. And what people did there with K2-18b is to actually argue about, is that the living room or is that the kitchen, right? And then the James Webb came, and that's like you don't look through the keyhole anymore. You open the actual door and you can look at the actual room. You get the broad spectrum. You get all the molecules. The water turned out not to be water. That was actually methane, CO2, other molecules I'm not going to mention because I don't believe them. Yeah, that basically opens up the whole discussion. It didn't turn out not to be a kitchen and not a living room, but a kind of a bedroom. And now the arguments, well, if there is a bed, it doesn't mean there is actually a bedroom, and it may be a kitchen with an actual bed. So you can imagine we will actually discuss this planet for the next decade or so. But we have the data, and we can now start really examining these kind of objects. Very, very exciting. Another example is this 55 Cancri E. This is kind of a super Earth, a few times the mass of the Earth, a very short orbit, only less than a day, I believe. It's I think 2,000 Kelvin or so. Yes, there are measurements. Now, this is again example. No, this is with MIRI, the long wavelength. There is actually absorption, CO2 absorption here at 4.4 micron. What's happening for the rest of the spectrum is not clear. A lot more data will be taken, but there seem to be an atmosphere. So we are more or less in this regime here. And the third example, which is very exciting, these are the TRAPPIST planets. First, TRAPPIST 1b was observed. This is very close to the host star. This is the hottest. Very much problem with the high energy and the high energy particles from the star. It doesn't seem to have an atmosphere. The second one, TRAPPIST 1c, may have an atmosphere, so maybe it's moving closer to this boundary limit, and hopefully in the next couple of years, James Webb will be able to measure some of the other planets which are further away, and hopefully we're getting into the actual regime here. Now, what is important here is that, you know, this is really, we are making an enormous jump, right? We're going from here, and suddenly there is a whole landscape of possible atmospheres are becoming available with the James Webb Telescope. There is, however, quite a debate on whether we will be able to reach more terrestrial-like planets or not. That will be very difficult. That will be really challenging, not only because of the James Webb, because of it's a relatively small telescopes relative to the telescopes I'm going to show you later, but also intrinsically transits and eclipse measurements. You do not separate the photons from the star and from the planet. So for every planet photon, you get hundreds of thousands, maybe up to a million of stellar photons. So this is really, the noise will always be driven by that of the star. The stars are not nice and stable. They do all kind of funky things. So that could be ultimately the limit of what this transit and eclipse measurements are gonna bring us. So there is actually one James Webb observation very recently that I think is I love it the most. It's such a fantastic, but to explain that, I need to first explain a little bit of a story, then you will actually appreciate more why I think that particular measurement is so nice. So what I'll first do is I'm going to introduce the next big project, and that is the extremely large telescope from the European Southern Observatory. We're all very well aware that the US friends are also pushing for two extremely large telescopes. That's a whole different story. We can actually discuss that during dinner, I guess. I will focus on the European project, and it is a fantastic project. This telescope is really a monster. It has a diameter of 39 meter, and it's built by 16 countries in Europe plus Chile. And I must say, I was looking for the flag of Norway, but I don't see Norway here. So maybe that's also something to actually discuss. I think this is the most exciting, one of the most exciting endeavors of modern physical sciences. And yeah, I really would appreciate if Norway could also join us in this. These are long-term projects. Now, the detailed study started in 2006. Site was selected in 2010. I think they blew up the upper part of the mountain in 2014. The structure of the dome started to be built 2018, and that will be ready in 2 years from now, so 2026. Technical first light of the telescope itself is expected in 2028. That will be also the moment the first instruments will arrive, and then it will take a while, and then hopefully everything will work. Now, how to show that's best is that you see at ESO website, they upload movies once in a while. They have a very beautiful drone movie of what the telescope is looking now. And I visited myself in April a year ago. Then they were still only building the lower part, and you should see now, this is just absolutely amazing. Just to give you an idea of scale, there are people here. Here, 1, 2. And this is part of the telescope mirror structure, support structure. I think there will be an outer ring on this as well. And we fly now over the out of the actual dome to give you an idea of the sheer scale. So the dome itself is the mirror is 39 meters. The dome is 82 meters high in northern Chile. This is one of the best sites in the world. And for my American colleagues. We had a discussion about this yesterday. What does 82 meters mean? Wait. So 82 meters is 262 feet and 11 inches. So the circumference of this dome is 292 meters. This is 319 yards, 2 feet and 3 inches. That means that the volume of the dome is 5,654 cubic meter. That is in gallons. No, sorry, this must be wrong. No. Going from meters to liters to gallons. Anybody, no one knows what an actual gallon is, right? So that's fine. Okay. Right. There will be a very rich instrument suite on the telescope. There is a first generations of instruments. There will be Mikado, Metis, and Harmony. I won't explain all the acronyms and all the instruments, only the ones in yellow, because those are really focused on exoplanet research. The second generation instruments will be Andes and Mosaic. Andes will be basically an espresso for the ELT. And then the ultimate exoplanet camera and spectrograph will be after that. So that will be a third generation instrument. It's called the PCS. And there's a lot of work has to be done. Also, we really want to know how the telescope works before we really gonna push. With this instrument, we want to push really to the limit of what the ELT will be able to do. What's maybe interesting to know for the American side is that the GMT, so that's one of the American ELTs, is planned to have a similar instrument, but then as a first light instrument. So that would be, it's not that then this PCS would be a lot earlier than what the actual Americans would be doing. So that would be very exciting to have around that time scale, to have actually two instruments that would be able to do this. So let me focus on Metis. This is an instrument that I know most about. The Netherlands is actually leading this with partners from Germany, Switzerland, Belgium, the UK, in Asia, and also the University of Michigan. It will have imaging from 3 to 5 micron, and also at 10 micron, and it will have a resolution spectrum of about 1,000. And what is very exciting for exoplanet research, in the end I will talk a little bit about that, is it will have a high resolution spectrograph of 100,000 between 3 and 5 micron, but as an integral field unit. So this will be very exciting. How far are we? The final design review was passed earlier this year. We really, the different parts all over the world are being built at the moment. Integration will start in a few months, will be done in Leiden, and the idea is to have it ready for Chile in 2028. Maybe it's good here to do one step back, and that is to realize, we want to do direct imaging. So this is, I told you about the transit and eclipses. You don't separate the light from the star and from the planet. But when you do direct imaging, you really, your angular resolution of your telescope, especially when you have a large telescope, can be enough to really separate in the sky the light from the planet and the star. So this will be very powerful. But there is a challenge, and that is, the star, you have the resolution of the telescope, which is governed by the wavelength over the actual diameter of the telescope. So the larger the diameter, the sharper you can look. But this is only in the hypothetical case. What you happen is the star emits the light and it travels for decades through space, and that you have a perfect wavefront, but then happens in the last millisecond when it arrives in the atmosphere, before it enters the telescope, it gets scrambled. And that means that your telescope, although perfectly shaped, cannot form a perfect image anymore. And you get a sort of so-called seeing disk, which is typically on the good side a bit more than half an arc second in size, and which is really, I believe, a factor of 100 or so worse than you would expect if you would have a perfect image. Now, there is a way to circumvent that, and that is you can measure the wavefronts and have a deformable mirror, and every, say, 1,000 times per second, measure the wavefront and have a mirror doing exactly the opposite to actually compensate for that. And that is a method that's been working on for 15 years or so, and people are getting better, engineers are getting better and better in this. Now, there are limits, the number of the actuators on how well you can deform the mirror, how fast you can do this. So these are really engineering challenges people are working on. Also, you always have to realize that the path through your wavefront sensor is different from the science path, so you get actually non-common path effect. So what you measure is not exactly what's going to happen in your image. And then there's always a thing that's called time lag. You measure it and then you apply it to your mirror, but that is, the info for that is old. So actually constantly the application that you do to your mirror is slightly wrong. So there is also a way the people are thinking about algorithm. How can we, from what has happened in the last few seconds, can we make a prediction what the atmosphere is doing in the next milliseconds or so? And then what has also been worked on in this field is second stage AO. You don't have one deformable mirror, but you measure what the leftover problems are in your image, and you use a second mirror to actually solve these. Now, these are all things that people are working on, which for the ELT will also be very, very important. Now, what is important is also I want to show is that how much a larger telescope helps when you do direct imaging. You know, when we think about transits or eclipse measurement, of course, a larger telescope gives you more flux, so that helps in building up the signal. But there is a second effect, and that has to do with the angular resolution and looking at the faint planet next to a very bright star. And I show that with this simple diagram. This is an 8-meter telescope. You have a seeing disk, you have the star, which is like this, very simple, and this is the planet. And actually the signal to noise of the planet is in most cases dominated by the stray light here. So the light which is still left off, left in the actual seeing disk. What happens now, if you go to a 39-meter telescope, you not only get 25 times more flux, but actually your angular resolution is 5 times smaller, and so actually the surface area of your image is 25 times smaller, meaning that any background effects will be 25 times smaller as well. So actually this goes not with d squared, diameter squared, but it goes with the diameter to the 4th power. And if you're close to the star, it goes even a lot faster. You call it d to the 5 or even more. So that is why doing this with a large telescope is so incredibly powerful. So this is what we can do now. Probably a lot of you have seen this very famous system, HR 8799. This is a movie taken over several years. You see 4 planets. But this is challenging. You have to realize contrasts which are reached now are about 10 to the minus 6. And that's actually not sufficient to look at normal planets that we see in our solar system, either through reflected light or through thermal emission. They're just too cold. And that means to see planets, you have to go to young stars, because young stars have young planets. They are still hot from their formation, and therefore the warm thermal emission we can still measure. But yeah, young stars are further away. So that means that, you can look at the young star, but you can only probe the really outer parts of any planetary system. So massive planets very far from the host star, as you can see here. This is 20 AU or even 40 AU away from the host star. So this is really, you're only going to catch now with the current system, you only catch the very odd, the very strange systems. Now we're going to move to the ELT. This is the moment that you can pick your 3D glasses. You can find them under your chair. I'm just joking. Okay, nobody looks. Very good. We have a bigger telescope. The resolution goes up with d squared. The speed goes up with d to the 4th. Now we can start to reach 10 to the minus 7, 10 to the minus 8. We can start to look at reflected light. We can start to look at thermal emission from cold planets. That means we don't have to go to these young systems anymore. Now we can look at our nearest neighbors. So I really see, this is the future of atmospheric characterization of planets. We're looking at the solar neighborhood, and there is one particular, now I go back to the James Webb, I think that's one particular system, Epsilon Indi, you can see it here, about here, one of the most nearby solar-type stars. It is a K star, so a little bit more, a little bit cooler than our own sun. And from radial velocity and direct imaging, it was already clear that something is orbiting this star. And now they had a look with the James Webb, Matthews et al. And what do they find? A planet. Here it is. This is a 10 and 15 micron, so this is a mid-infrared measurement of one of the most nearby stars, 3.7 parsec. That's the age of our sun. The temperature of the planet, 275 Kelvin. So this is really in the cold regime. It's in an orbit at about 15 AU, so between Saturn and Uranus. And you can, from models, estimate, okay, what kind of mass would you expect for this age, and so much thermal emission. It's about six Jupiter masses. Now you can ask yourself, so how far away are we to measure the system from the ground? Will we be able to do this with the ELT? It turns out there's also already VLT, so the current 8-meter telescope. A few years ago, they had 4 hours of observations, and they went back to the data. Look at that. I tried to do this on the same scale. They have an image. So already from the ground with an 8-meter telescope, you can see this planet. So this is very exciting. Now this is 4 hours with the ELT being d to the 4th power. So we're talking about more than 500 times faster. This will be in 30 seconds. You will actually get this image. And there's more. You can scale this if you do this 4 hours. Of course, the resolution will be a factor 5 better. So we have an image. So this would be at the same level as here. This would be actually a 275 Kelvin planet of 2 Earth radius at 3 AU. So this is now with simple, relatively simple direct imaging with the ELT, you can already range this. Very good. I have to hurry up a little bit. I'm going to talk. So this is basically the things you can do with classical imaging. And there's one thing in the last few minutes that I have. I want to focus on something I've been working on for many years. That is high-resolution spectroscopy, because in particular the combination of high-resolution spectroscopy and direct imaging is very powerful. This was already recognized by Sparks and Ford more than 20 years ago. Under different names, it has been invented and reinvented by many people. And it works as follows. This is a typical image that you get from an adaptive optics system and a direct image. Here's the star is blocked, and here is the planet. And what we would like to do is, this is very far out from the star, we'd like to find planets here in this part. But you see all these residual, this is residual starlight that is not corrected well by the instrument and by the exotelescope. There is no way to tell whether a blob here is a real planet or whether it's residual starlight, except if you have a spectrum of the light. Of course, the light from the star, the spectrum of the star is very different from the spectrum of the planet, because the temperature of the two is so different. So what you can do, and we just have an example here, a real data example with the resolution of 4000, works much better at a higher resolution of beta Pictoris b. This is the star, the planet is somewhere here, and this is the white light. You don't see anything there. But actually, this is not an image. This is an integral field unit. So from every pixel here in this image, we have a spectrum. This is completely dominated by starlight, completely in the stellar halo. But we know the spectrum of the star very well. It should be the same in every pixel. So we can remove that starlight as well as possible. And what we then do on the residuals of each pixel, we look for a signature of the planet. And we do that with the cross correlation with a planetary model. And what happens, so you do that for every pixel and you look at, okay, what kind of amplitude do I get? And then we get this. So here we see a very strong signal. This is for a particular model. And I think this, you can change the exoparameters and you see the signal become stronger or less strong. So that means you can really probe also the atmospheric properties of these objects. 1 minute. Yes. So this is one example, just an example of if you do this at high resolution, This is already for a decade ago. There's not an integral field unit yet. MATIS will be the first high-resolution integral field unit that can do this at the resolution of 100,000. We have a slit, but if we know where the planet is, we can put the star and the planet on the slit like this. We do the same game. We remove the starlight. This is now the position on the slit, and this is the signal. You now get also you can measure velocities. What you see here, this is the planet position, and you see, hey, this is a signal from carbon monoxide. It is blue shifted, and that's because this is an edge-on orbit. The planet is moving like this, and we measure it while the exoplanet is here. So it's moving towards us like that. You see a radial velocity is about, I believe, 15 kilometers per second, and it's broad. And the broadening comes from the spin rotation of the exoplanet. So it tells us something about the length of day on this exoplanet. Now, I had a few other examples. You can ask me during dinner. This is nice. This is a recent work. The cryo spectrographs on the VLT that we work with has been upgraded. So 8 years later, we did the measurement again. And now the planet is on the other side. So it was like this. And now it's moving away from us. And you see that here. So now this is the stellar velocity. Now actually the planet appears on the other side. We have it's moving away from us. And so it's very nice. It's also a way to probe the orbits. Now, there's this is just an example of what you can do. We do have a large survey what happens if you get very high signal to actually noise measurements. What kind of properties can you actually derive? We're doing quite a lot of isotope work. This is actually a slide just for Jonathan telling that my review article is almost done. I have another 2 weeks. So this will all combine. So this is the roadmap. We have MATIS 2028, we have Andes, we have the PCS, and then to really get to twin Earth planets, we have to go to the Habitable Worlds Observatory. Maybe somebody else will have time to talk about that. I just want to leave up the takeaway points. When will transmission eclipse spectroscopy hit its limit? At some point, we will reach a limit there. I really think the future of exoplanet characterization is direct imaging. The ELT will provide a major advancement for the next decades, and at some point we will hopefully have something like the Habitable Worlds Observatory or a mid-infrared interferometry to characterize the true Earth twins. Thank you.